Hello, welcome to the assembly training. We're going to start with a quick introduction. First, what's the goal of this training? It's basically getting you able to read assembly. Reading is what we mostly care about because that's what we mostly do as vulnerability researchers. You may occasionally need to write some, but very rarely. Why is this necessary when we have decompilers? There are a few reasons. Decompilers are great. The vast majority of the time, you will be looking at the decompilation rather than the disassembly, but they're not infallible. If your program does something a bit odd, maybe employing some optimizations, using handwritten assembly or an obscure instruction, then the decompiler can produce inaccurate output. So you need to consult the ground truth, which is the assembly. Also, for exploit development, you often need to read assembly. Say you're forming a ROP chain or whatever. Also, you might end up dealing with an obscure architecture that doesn't have a decompiler. And once you know one assembly language, many of the same concepts apply to all of them. We're going to start by focusing on ARM64. There are a couple of reasons for this. Firstly, it's one of the most popular architectures out there. Android, iOS, macOS, now all of that's going to be running on ARM64. And it's also relatively simple and consistent, so it's easier to teach as a starting point. After looking at ARM64, we're going to look at ARM32 and x86-64, mainly in the context of how they're different to ARM64. These three architectures combined should give you fairly good coverage of the common things you'd see as a vulnerability researcher. The general structure is going to be some of me talking, followed by some exercises, and repeating that over and over again. So in terms of the exercises, there'll be two main types, either reading a snippet of assembly and answering some questions about it, or writing some assembly to perform a specific task. There's regular and bonus questions. The regular questions are sort of reinforcing the things covered in the slides. The bonus questions are mainly there just for a bit of fun. They might deal with instructions that I haven't specifically talked about, or just be interesting problems of how you can solve things in fewer instructions, things like that. You're sort of not expected necessarily to do the bonus ones, but they're there if you want to. Everything's automatically marked. You'll have to follow the setup instructions for setting up a local Prairie Learn instance and accessing the course through that. It should be fairly simple. All right, so let's start with the basics of ARM64. First, what is it? It's a computer architecture designed by the ARM company. They sell their designs to other companies like Apple or Qualcomm, who integrate those designs into their own processors and get them fabricated. You may see it referred to by a few names: ARM64, AArch64, ARMv8A, or like ARMv9A. The A stands for application. It's 64-bit, meaning that most instructions operate on 64-bit integers, and it's possible to address 2 to the 64 bytes worth of memory, so that's 18 exabytes or something. Instructions are a fixed length, always 32 bits, and it's RISC, which is reduced instruction set computing, basically meaning it focuses on having a smaller, simpler set of instructions that can execute faster and with lower power consumption. For reference, this is a link to a list of instructions. We're going to look at the most common ones today, but there are a lot, and we can't go through all of them. So we're going to start by looking at the instruction layout. Here's an example of what a typical instruction might look like in ARM64. You've got the opcode in orange, followed by some number of operands in blue. The opcode is what operation is this instruction actually performing? Is it adding, subtracting, multiplying, comparing, jumping somewhere, loading some value from memory? That's what the opcode is. Operands are the inputs and outputs to the operation. In ARM, more often than not, these will be registers. So here, x0, x1, x2, they're all general purpose registers. They can be other things, and we're going to explore some of those as we progress. For basic instructions, the first operand is generally output, and subsequent operands are generally inputs. So this instruction is like saying x0 is equal to x1 plus x2. Let's now take a deeper look at general purpose registers. Registers are basically small, fast memory locations that can be operated on by instructions. In ARM, most instructions can only operate on registers. If you want to perform an operation on some numbers, first you'll need to get those numbers into registers and then perform the operation on those registers. In ARM64, there are 31 general purpose registers numbered from 0 to 30. They're all 64-bit. If you reference them with the X prefix, e.g. X0, then you're using the full 64 bits. But if you've only got small numbers and decide you only need to use the lower 32 bits, you can refer to them with the W prefix, so W0, W1, W2, etc. And in those cases, instructions might execute slightly faster. So let's look at the basic arithmetic instructions. These are more or less as you'd expect. We've already seen add, sub is for subtract, mul is for multiply, and then there's udiv and sdiv, which is for unsigned and signed division, which brings us onto a fairly important point, which is that registers in and of themselves don't have any sort of signedness. It's just 64 bits of data. It's up to the instruction to interpret that either as signed or unsigned. So say x0 contained this value. Depending on the instruction, it could either be interpreted as unsigned, so that would be this 18 quintillion and something, or signed in 2's complement, where it's -3. The good thing about 2's complement is that for addition, subtraction, multiplication, the signed and unsigned operations are the same. That's why there's only one version of add, sub, mul. But for division, it's different. Say we wanted to divide 6 by x0. Well, if we chose the signed interpretation, we would expect the answer to be -2. But if we selected the unsigned interpretation, we'd expect the answer to be 0. So that's why there are 2 variants for this instruction. Before we look at any more instructions, it's probably a good idea to take a look at a couple more operand types. The first of these is immediate operands, which represent a constant value. When these are written in assembly, you use hash prefix number. So, for instance, this instruction increments the x0 register. There are a couple more important things to remember about immediates. First, not all instructions accept them. Add and sub do, but mul does not, for instance. Also, you're limited in their value. For example, in the add instruction, the immediate is limited to 12 bits. And that's just because all instructions in ARM64 are 32 bits, which has to include the opcode, register operands, and the immediate value. So you're just limited in what you can fit into that size. Second operand type is the 0 register, or XZR. As the name suggests, this is a register that is always 0. It's very helpful because you can use it almost anywhere in place of a general purpose register. Even in instructions that don't allow an immediate operand, you can always get 0 basically. This is in fact the reason why there's only 31 general purpose registers. Instructions encode a register as 5 bits, so that's 32 possible values, and one of those is reserved for the 0 register. And you've already seen the 0 register being used, even if you haven't realized it, and that's because the mol opcode is really just shorthand for madd, with the 4th operand as the 0 register. You'll see quite a few of these pseudo instructions in the ARM64. They help to keep the number of real opcodes down. Generally, you don't need to think about them too much. Disassemblers are smart enough to output the simpler pseudo instruction if certain conditions are met, and these conditions are even listed in the ARM documentation. So, for instance, if madd's last operand is the 0 register, then mol is preferred, and that will be what the disassembler shows you. Alright, time for the first set of exercises, which should be ARM64 Basics 1. Alright, moving on. Now let's look at bitwise operations. These work more or less as you'd expect, but the naming is a bit odd. So first there's MVN, which is bitwise not. I think it might stand for move not, maybe. This flips the bits of the input and stores that in the output. Quite simple. Second there's OR, which is bitwise OR, where each bit in the output is 1 if either of the corresponding bits in the input was 1. Then there's AND, which is bitwise AND. So each bit in the output is 1 if both of the corresponding bits in the input was 1. And finally there's EOR, which is bitwise exclusive XOR. Here each bit in the output is 1 if the corresponding bits of the input differ, basically. Then there's shifting operations. First there's LSL, which is logical shift left. Here every bit is shifted left by a specified number, and that sort of gap is filled in with zeros. Then there's LSR, which is exactly the same as LSL, but shifting right instead. And after that there's ASR, which is arithmetic shift right. And to explain this, it's probably easiest to look at an example. So say we have this 8-bit number. Interpreting this as signed, it is -4. And if we perform a right shift by 1, then we expect that to divide the number by 2. But if we perform a logical shift, then the number becomes 126, because the most significant bit has been filled with 0. With an arithmetic right shift, however, bits are filled with whatever the most significant bit was before. So negative numbers are handled correctly, and we get the expected result of -2. Finally, there's ROR, which is rotate right. So here bits go from one end and come back round the other side. There's no rotate left, since the same result can be achieved with a rotate right. And that brings us to the final part of this section, which deals with various move instructions. With the instructions we've already seen, you might be able to think of ways of copying one register into another register. For instance, you could add where one of the inputs is 0, or you could multiply where one of the inputs is 1. For convenience, ARM64 provides this MOV pseudo instruction, which maps to OR where the second operand is the 0 register. So that covers moving one register to another. But what about moving an immediate value into a register? For that, there are 2 helpful instructions. The first of these is move Z or move 0. This allows you to move a 16-bit immediate into a register and zero the rest of the register. Optionally, you can provide a left shift that should be applied to that immediate before it's placed into the register. The values for that shift can be 0, 16, 32, or 48. The second instruction is move K or move keep, which is the same as move Z, but instead of zeroing the rest of the register, it keeps it as it was. So by combining these instructions, it's possible to move whatever immediate value you want into a register. And let's see an example of that. So say you wanted to move this 133337 value into X0. And in hex, that value is 20,839. So first, we can use move Z to set the least significant 16 bits to 0839 and 0 the rest. Then we can use move K to set the second to least significant bits to hex 2 and leave the existing hex 0839 as it is. That brings us on to the second set of the exercise, which is ARM64 Basics 2. Okay, so let's move on to control flow. You might have noticed it's quite hard to make a useful program just executing one instruction after another. You really need some sort of conditional branching to do anything interesting, which is what we'll cover in this section. So let's take a look at the most basic example, which is an infinite loop. We label a location in our program as foo. A label is just some text at the start of a line followed by a colon. And then we use the B or branch instruction to jump to that foo label. And this forms an infinite loop since the location we are jumping to is the branch instruction itself. It's important to understand that labels are just a convenience when writing assembly. When the assembly is converted to machine code, the concept of a label disappears. Instead, the branch will basically say jump this many instructions forward or jump this many instructions backward. Disassemblers will typically convert this relative branch target to an absolute address to make it easier to see where it's going. It's probably worth, at this point, briefly talking about the program counter, or PC register, which points to the instruction currently being executed. It isn't like the general purpose registers, it can't be used in add or whatever, but this is what the branch instruction modifies, and it's worth knowing about for debugging, etc. Now, an instruction that just jumps somewhere isn't that useful. To make things like if statements and for loops, you really need to only jump if certain conditions are met. And in ARM64, this is achieved in two parts. First, there's the CMP instruction, or the compare instruction, which compares two registers. And then there are conditional branches, which may jump or may not, depending on the result of the comparison. So, for example, BEQ will only branch if the registers were equal. There are different greater and less than conditional branches, depending on if you want to treat the registers in the comparison as signed or unsigned. The naming is a bit confusing. Lower, lower or same, higher, higher or same for unsigned, less than or equal, greater than or equal for signed, but you don't need to memorize any of this. There are also some instructions that merge the comparison and branching into one. So CBZ will jump to the label if XT is 0, and CBNZ will jump to the label if XT is non-zero. They stand for compare and branch on 0 and compare and branch on non-zero. There's also TBZ and TBNZ. These test if a specific bit in a register is 0 or not and branch accordingly. You may see references in the documentation to CB condition instructions, which merge the comparison and branch into one. but these were only added in ARM 9.6, so they haven't actually been implemented into any chips yet. So it will probably be a few years before you actually see any of these instructions being used. Let's take a look at a couple of examples. First, there's this. You can maybe pause for a few seconds and see if you can work out what this is doing. Basically, it's an if statement to set x2 to the greater of x0 and x1. So first we compare x0 and x1. If x0 was higher, then we branch to the x0 higher label, and x0 is moved into x2. If x0 wasn't higher, then we continue on and move x1 into x2 instead. We've got this unconditional branch to end so that we don't roll on to the x0 higher logic. Now here's a second example. Again, can you work out what this is doing? So this is finding the factorial of x0 and storing it in x1. If you don't know, factorial is multiplying all the positive integers up to and including a positive integer. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. So let's walk through, say that x0 starts at 3. First there's a bit of setup. x1 is set to 0. Then we compare and branch if x0 is equal to 0. It isn't, so we continue on and set x1 to the product of x1 and x0. Before this, x1 was 1 and x0 was 3, so after this, x1 ends up being 3. Then we subtract 1 from x0, storing the result in x0, so x0 is now 2. And we branch to the loop label and go through again. So x0 still isn't 0, so we continue on. We've got the multiplication. This time x1 is 3, x0 is 2, so x1 ends up being 6. We decrement x0 and loop again. At this point, x0 is 1, still not 0 in the multiplication. x1 is 6, x0 is 1, so x1 stays at 6. We decrement x0 again, and this time when we loop back, x0 is 0, so we take the branch to end and the program is concluded. Up until now, we've glossed over what the compare instruction is actually doing and how it enables conditional branches to work. So the compare instruction is actually a pseudo instruction for subs, where the result is discarded by sending it to the 0 register. Subs stands for subtract and set flags, and it's that setting flags part that we really care about. Flags is a special purpose register where only 4 bits are used, and each of those bits is set or cleared depending on the result of flag setting operations like subs. And it's somewhat important to understand what these bits represent. So first, there's the negative bit. This is set if the result of the operation interpreted as signed was negative. So basically, if the high bit of the result was set to 1. Next, there's the 0 bit. This is very easy. This is set when the result is 0. The next two are significantly harder to understand. On this slide, I'll talk about how they make intuitive sense when talking about addition. On the next slide, we'll talk about how you can think of subtraction in terms of addition and use that to make sense of how the CMP instruction sets flags. So there's the carry flag, and this is set if the result of the unsigned operation is too big to fit into the register. So if you're adding 2 very large numbers and the result is too large to fit in 64 or 32 bits, whichever you're dealing with, then the carry flag will be set. And finally, there's the overflow flag, which is set if the result of a signed operation is too big to fit into a register. So this happens if you're adding 2 very large positive numbers or 2 very large negative numbers. So let's look at subtraction in terms of addition. Obviously, a minus b is the same as saying a plus negative b. So how do we negate a 2's complement number? How do you flip the sign? You may recall from A-level computer science that you flip the bits and add 1. So say you have positive 3, you flip the bits and end up with negative 4, and then you add 1 and end up with negative 3. So negative b is just the same as saying not b plus 1, meaning a minus b is the same as saying a plus not b plus 1. And when thinking about how the CMP instruction sets flags, this is the operation you need to consider. And it's the same no matter if you're treating registers as signed or unsigned. And thinking about this, you can start to think about how the various branch conditions work. For instance, there'll be an unsigned carry if the first operand is greater than or equal to the second. Just for reference, here is how the conditions relate to flags. You don't need to remember these or anything. In fact, the majority of the time, you don't need to care about flags at all. You'll just be looking at a compare followed by a branch where everything makes intuitive sense, but occasionally you may need to think about them. This brings us on to the next set of exercises, which should be ARM64 Control Flow 1. Now, CMP and subs are not the only instructions that set flags, and we're going to look at a few of the other ones here. Just be wary that the branch conditions only really make intuitive sense when you're dealing with the subtraction operation. So first there is CMN, which stands for compare negative, because you can make the conditions make sense if you think of the second operand as being negated before the comparison. This is an alias of adds or add and set flags. Then there is TSD or test. This is an alias of ands or and set flags. Here only the EQ and NE conditions really work to check if the result is 0 or non-zero. Then there's CCMP and CCMN. These stand for conditional compare and conditional compare negative. They're quite interesting because they allow you to chain comparisons without branches. So basically they'll only perform the comparison if cond is met. Otherwise they set NZCV, the flags, to the immediate value you specify. And we'll take a look at an example of this on the next slide. And finally, there's ADCS, SBCS. These stand for add or subtract with carry and set flags. And these use flags in two ways. First, it uses the carry flag in the addition or the subtraction. So, for example, if the carry flag is set in an addition, it will be like adding an extra 1 to that addition. And it will also set the flags, including carry, based on the result of the addition or subtraction. And these instructions are very useful for dealing with integers that are too big to fit into a single register. And we'll also take a look at an example of this. So on to the examples. Here's the first. Again, take a second, pause the video, and see if you can work out what this is doing. So it's basically performing this comparison. It's adding an integer spread across x12, x11, x10 to one spread across x22, x21, x20, and storing the result spread across x2, x1, x0. How's it doing this? First, there's an add and set flags with x10 and x20, storing the result in x0. So if the result was too large to fit in x0, the carry flag will be set. Then there's an add with carry and set flags between x11 and x21, storing the result in x1. So if the carry flag is set, then an additional 1 will be added to the addition to account for that carry. And this may also set the carry flag if the result was too large. And then there's a final ADCS, which does the same as the previous, but with different registers. Now, for the second example, again, take a minute and see if you can work out what this is doing. So it's basically performing this comparison, checking if x1 is greater than x0 and less than x2. It does this by first comparing x0 and x1, and then conditionally comparing. So If x0 is lower than x1, it compares x1 to x2. Otherwise, it makes it so only the carry flag is set. And then there's a branch if lower. Since this is only taken when the carry flag is cleared, it will only occur if x0 is less than x1 and x1 is less than x2. Now, branches are all well and good, but because they make pipelining more difficult, they can slow your program down. So it's best to avoid branches where you can. You've already seen one example of this with CCMP, but let's take a look at some others. First, there's CCell, or conditional select, which is quite simple. If cond is met, then it will move xn into xd, otherwise it will move xm. Then there's CSInc, or conditional select and increment, very similar to CCell. If cond is met, it will move xn into xd, otherwise it will move xm, but incremented by 1. CSInv, or conditional select and invert, this does the same, but instead of incrementing y1, it performs a bitwise not. And CSneg, or conditional select and negate, instead of incrementing by 1, it negates xm. Final thing we'll look at in this section is how functions are sort of implemented. We'll cover this in more detail in the next section where we'll talk about memory and the stack, but this is just a quick introduction. So here's a very basic example of a function. There are two new instructions here. The first is BL, or branch and link. This will store the address of the next instruction, so where these dots are, in the link register, and then jump to the specified label. And ret, or the return instruction, will jump to the link register. So in this example, we call add function with BL. The add instruction is performed, and then we return just after that BL with ret. The link register isn't anything special, it's just another name for the general purpose X30 register. So now on to exercises. These are ARM64 control flow 2. Now, registers are all well and good, but you're very limited in the amount of data you can deal with, and it's difficult to properly implement functions. That's why in this section we're going to look at memory and the stack. Let's start by looking at the basic memory instructions. First, there are LDR and STR. LDR stands for load register. It will load a value from memory into XT. STR stands for store register. It stores XT in memory. Then there's LDP and STP, which are very similar, but load or store two registers at once. They stand for load pair and store pair. But where do these instructions load or store from? What are these question marks? They can be a few things, which we'll look at now. The most basic case has this syntax, where the contents of xn plus the optional immediate form the memory address that you want to load from or store to. This variant doesn't affect xn at all. But if you put an exclamation mark after it, you get the pre-index variant, which stores the memory address back in xn. There's also the post-index variant, which only uses the contents of xn to get the memory address, but after the access, the immediate is added and the result is stored back in xn. You can also load directly from a label. Just like jump, when this is assembled, it becomes a relative address, and disassemblers generally display it as absolute. And you can add two registers to get the address as well, with xm optionally being shifted left by 3. Let's take a look at some examples. For all the examples, let's say that there is this data at memory address 0x1000, and x0 contains that address. Keep in mind that data accesses are little endian. I think in theory the ARM64 specification does support big endian data accesses, but I don't know if any real hardware supports it. So for the first one, take a second and see if you can work out what would be in x1 and what would be in x0 after this instruction. So this is the answer. Let's take a look at what's happening. So first, 8 is added to x0, which is hex 1000, so you get hex 1008. So we load from hex 1008 and put that value in x1. Remember the endianness, we tend to show registers as big endian, so it needs to be swapped. There's no exclamation mark, so x0 is unaffected. Here's the second example, same thing. What's in x1 and x0 after this happens? But yeah, this is very similar to the first one, but because it's got that exclamation mark there, the OX 1008 is stored back in x0. Finally, for this one, again, what's x1 and x0 after it executes? So this time we do the load using just x0, so just OX 1000, and then we add 8 and store it back. There are also different variants for this if you only wanted to load or store 8-bit, 16-bit, or 32-bit values. Here's a table. There are two different loads. The unsigned variant, where the loaded value is padded by zeros to fill the register, and the signed variant, where the loaded value is padded with a signed bit. So say you had a byte value of OXFF, that's -1 if you interpret it as signed. LDR SB will pad with the 1 bit so that the register is still interpreted as -1 signed rather than 255. For the 32-bit unsigned load and store, you can just use the W registers. One last thing before we move on to the exercises. There are a couple of instructions that are commonly used to get addresses into registers. First, there's ADR, which stands for address relative, and it will load the address at label into XD. When this is assembled, just like other label instructions, it becomes relative, and disassemblers will show the absolute address. Then there is ADRP, which stands for address relative page. This will load the address from the page containing label into XD. A page is OX 1000 or decimal 4096 bytes of memory, and it will always be aligned, so the last 3 nibbles of the address will always be 0. And because of this, ADRP lets you reach 4096 times further than ADR. It's common to use ADRP to get the page of an address and then add with an immediate to go from that page to the actual address. So, on to the exercises, which are ARM64, memory and stack 1. So now let's look at how the stack works on ARM64. I'm assuming people already have a basic computer science understanding of how a stack works. Here's an example of what the ARM64 stack might look like. SP is a special register that points to the top of the stack, and the stack is full descending. The full part means that SP points to the most recently pushed item, and the descending part means that it grows from higher memory addresses to lower memory addresses. It's important to note that the stack must always be 16-byte aligned, so basically the least significant nibble of SP must always be 0. Not doing so causes faults. How is SP manipulated? So in some instructions, basically the stack pointer takes the place of the 0 register as that sort of special 30-second register choice. This includes the memory instructions, so LDR, SDR, LDP, STP, as well as the immediate variants of add and sub. Now, with this information, you might already be able to work out how you can push and pop from the stack in ARM64. So to push, you can just use STP. You decrement 16 from the stack pointer and then store 2 registers there. And to pop, you can just use LDP. So load 2 registers from the stack pointer, then increment it by 16. Now let's take a look at how the stack is used by functions. So whenever a function is called, it will create what's known as the stack frame at the top of the stack. A frame might look a bit like this. Typically, it will contain some space for things like local variables, as well as what the link register and frame pointer were at the start of the function. We've already looked briefly at the link register, which holds the return address of the function and is really just x30. Saving and restoring it like this means that you can call function after function. The frame pointer is new. It's really just another name for the general purpose x29 register. Most of the time it's useless since compilers do everything relative to the stack pointer, but it always points to this saved frame pointer link register pair, which is useful for getting a backtrace of all the functions that have been called during debugging. It's sometimes required if you use features like variable length arrays or alloc, basically where the compiler can't know the size of the stack frame, but those features are generally discouraged anyway. You might hear that the frame pointer always points to the bottom of the current stack frame. It does in this example, but we'll see that this isn't always the case. The first set of assembly here is an example of a function prolog. So this runs at the start of the function. So here the stack pointer is decremented to make space for the stack frame. The frame pointer and link register are stored at the bottom, and the frame pointer is updated to point to the saved frame pointer. Second set of assembly instructions is an example of an epilogue, which runs at the end of a function and basically undoes everything in the prologue. So SP and L are restored, and the stack pointer is incremented to remove the space for that frame before returning. Here's a different style of stack frame, where the saved frame pointer and link register are instead at the top. In more optimized code, this variant's often used because it makes it possible for the prologue and epilogue to be shorter. Which one you get depends on a number of factors, so it's really just important to know that stack frames don't always look the same. Leaf functions, for instance, those are functions that don't call any other functions. They generally don't bother with saving the frame pointer and link register at all. Now let's quickly look at the calling convention. Basically, how does a function expect its arguments and where does it put its return value? So for the arguments, first you put them in the registers x0 to x7 inclusive. So the first argument goes in x0, second x1, etc. When you get past x7, you start putting them on the stack. So the 9th argument at the top of the stack, 10th below it, etc. The return value is generally put in x0, but if it's too big to fit in a single register, then it will be split between x0 and x1. If it's too large to fit into 2 registers, say you're returning a structure or something, then it's up to the caller to create space on their stack frame and provide a pointer to that space in x8, which also has the special name of XR, or like indirect return register. Another thing that's important is how the other registers are handled. So x9 to x18, it's up to the caller to save those if they contain anything important. The callee is free to overwrite them. x19 to x28, however, that's the responsibility of the callee to save. So if the callee wants to use any of these registers, they must save them at the start of the function and restore them at the end of the function. Last thing to say that's important is that these are just conventions. Compilers might not obey them, especially when there are heavy optimizations. The same applies to the call stack. Prologues and epilogues can vary. They may not do anything on the stack, they may just use registers, so just be aware that things won't always be totally clean. And yeah, onto the final set of exercises for ARM64. For the final part of the ARM64 section, we'll look at some miscellaneous things. First off, system calls. These are the main way that userland programs interact with the kernel. So they're needed for many things like displaying text, getting user input, creating a file, starting a new process, exiting from the current process, etc. Often if you're writing code, you'll use these indirectly through a library like libc. But take puts, for instance. In Linux, all that's really doing is measuring the length of an old terminated string, adding a new line, and then using the write system call with the standard output file descriptor. So how do these syscalls work in Linux? Well, you put the syscall number in x8, in the x8 register. You can find tables online for what numbers map to what system calls, like what maps to write, what maps to read, and the arguments for that. The arguments themselves go in x0 to x5, and to actually execute the system call, you use this svc0 instruction. This calls the supervisor, which is the Linux kernel. After the syscall is finished, the return value is put in x0. So let's take a look at a quick example. See if you can work out what this is doing. You'll probably have to look at a syscall table. So this is basically using the read syscall to get 16 bytes from standard in and store that at the memory address OX1000. So essentially getting 16 bytes of user input. Now we move on to things that make our lives as vulnerability researchers harder. And the first of these is BTI, which stands for Branch Target Identification. This is basically a way to tell the program where the valid locations of a branch are. If you try to branch to an invalid location, there will be a fault, which means, say we're trying to exploit something which overwrites a function pointer. Now we can't just point it to the middle of a function, and that vastly reduces our options for exploitation. How is it actually implemented? Indirect branches are what's called BTI settings instructions, which means that they set something in the processor such that if the next instruction to execute isn't a BTI clearing instruction, there'll be a fault. The BTI instruction is an example of a BTI clearing instruction. You might see this at the start of functions or entries in a jump table. It's followed by J or C or both, depending on if this is a valid target for jumps or calls, or both. This instruction is in NOP space, so a program compiled with BTI will still work on processors that don't support it. One important thing to note is that the RET instruction is not BTI setting, and that's because you don't want to have BTI clearing instructions after every call. That would increase your code size by quite a bit, and if there are loads of BTI clearing instructions, that partially defeats the point of limiting where you can branch to. That being said, we do still need to protect the link register from being overwritten, and that's where PAC or pointer authentication code comes in. And this is basically a way of signing a pointer and then later on verifying it. So if it's been overwritten by an attacker, then the signature will no longer match and there'll be a fault. This is most commonly used to protect the link register, but it can also be used to protect things like vtables. So how is PAC implemented? A pointer is signed by cryptographically combining the pointer itself, a key. Each process has 4 different keys it can use for PAC, an A and B key for instructions and an A and B key for data, as well as some context, which might be like the stack pointer. This is basically something to mitigate the chance of swapping one sign pointer with another. And that signature is stored in the top 16 bits of the pointer, which is fine since generally only 48 bits are used for addressing. When it comes to verifying, the signature is calculated again and compared to those high 16 bits. This is a common PAC signing instruction that you might see at the start of a function. The IA stands for instruction key A, and it's used to sign the link register with the stack pointer as context. This instruction is also BTI clearing, so you only need one instruction at the start of a function for both PAC and BTI. And this is a common PAC verifying instruction. It stands for return authenticated using key A. It will verify a pointer signed with that instruction above, return if the verification is successful, or fault if not. And that's about it for ARM64. Alright, let's move on to ARM32. First, what is it? It's sort of an older version of ARM64, but it's still actively developed and mainly used in microcontrollers now. You might see it called AArch32, ARM V7A or M. The A stands for application, the M stands for microcontroller, and also ARM V8M is 32-bit as well, and ARM V9M. So yeah, it's 32-bit, which means that most of the instructions operate on 32-bit integers. You're also limited to 4 gigabytes of memory. And the instructions can be 32 or 16-bit, depending on the mode. And we'll look at modes later on in this section. It's RISC, just like ARM64. And here are the list of instructions. So the first big difference is registers in ARM32 are 32-bit. And there are only 16 of them, named R0 to R15. These are the main ones that also have special uses. You'll notice that the stack pointer is now just a regular register, as is the program counter. In ARM64, you could only change the program counter with branch instructions. In ARM32, it can be used in a lot of instructions, which means you can do weird things like just adding to the program counter. There's also no zero register. Another big difference in ARM32 is that there's two different modes. There's ARM mode and thumb mode. ARM mode always has 32-bit instructions. It used to be that thumb mode only had 16-bit instructions and was sort of a far reduced instruction set compared to ARM mode, but then thumb 2 was introduced, which added a lot of 32-bit instructions to thumb, and now they're basically equal in what you can achieve with them. Programs don't need to just contain all ARM mode instructions or just all thumb mode instructions. They can contain a mix. And we'll talk about how you can switch between the two modes in the control flow section. Another big difference comes when loading immediates into registers. In ARM64, we had move Z and move K. In ARM32, since the registers are only 32-bit, things are a bit simpler. So there's just the move instruction with an immediate. This sets the lower 16 bits of a register and clears the rest. And you may see this written as move W, standing for move word. There's also move T or move top, which sets the high 16 bits of the register. These exist in both ARM and thumb mode. These are examples of 32-bit thumb instructions. Other than that, the basics are mostly the same. Instructions mainly have the same syntax. The arithmetic instructions work the same, although in ARM32 in general they have fewer pseudo instructions because of the lack of zero register, so mul is its own instruction rather than just an alias of madd. The bitwise instructions work the same, the shifting instructions work the same, although in ARM32 these are all aliases of move, and move for moving things between registers works the same, although now it's no longer an alias of OR. Okay, so on to the ARM32 basics exercises. Alright, let's move on to control flow, starting with the basic similarities and differences. So the basic branch, compare, and conditional branch are all the same, both in ARM mode and thumb mode, although the conditional branch no longer has a dot between the B and the condition. Also, CMP is now its own instruction rather than alias. CBZ and CBNZ only exist in thumb mode. The flags work the same. CMN and test work the same. CCMP and CCMN don't exist in ARM32. We'll see why they're not really necessary in a minute. ADCS and SBCS work the same. And none of the conditional selection instructions exist. And again, we'll see why those aren't really needed. And the reason for that is this first major change, which is that in ARM32, basically all instructions are conditional, which means that you can just put a condition code like EQ or LT after any instruction, and it will only execute if that condition is met. Now, there is a caveat when it comes to thumb mode, but we'll look at that in a bit. For ARM mode, it just works like this. So while in ARM64 we had these conditional comparison and conditional selection instructions to avoid branches, those aren't really needed in ARM32 because every instruction can be conditional. So let's take a look at a couple of examples. First, can you work out what this is doing? So yeah, it's basically equivalent to this code. We compare R0 to 0 and move R2 into R1 if they're equal. If they aren't, we instead move R3. In ARM64, you could achieve this similar functionality with C-cell, but in ARM32, every instruction being conditional means it's a lot more intuitive and you can achieve a lot more without branches. Second example, how about this? So this is equivalent to this comparison. Again, in ARM64, you could achieve the same with CCMP, but this is a lot more intuitive. Now, if you think about the fact that thumb instructions are generally 16 bits, you realize that you can't really waste 4 bits of those to make every instruction conditional in the same way that ARM mode does. Branch is the only instruction that can be conditional in the same way as in ARM mode. For the others, you need to use the IT or if-then instruction to make them conditional. The IT can be followed by any mix of up to 3 T's and E's, and the T's and E's, including the first T, maps to subsequent instructions that are conditional on cond in the case of T, and are conditional on the inverse of cond in the case of E. We'll look at some examples of this because it's a bit confusing. So this would work in ARM mode, but to make it work in thumb mode, see if you can work out what IT instructions would need to go where. Okay, so we have an EQ, an NE, and a GT condition. EQ and NE are opposites of each other, so we can make those work with an if-then-else, an ITE, and we need a separate if-then, a separate IT for the GT. What about this? Can you work out what IT instructions you need? So here we have HS, LO, HS, HS. HS and LO are opposites, so you can make this work with a single if then else then instruction, an IT, E, TT. The final thing we're going to look at in this section is changing between ARM and thumb mode. And this sort of ties into functions as well because the BLX instruction is one of the main ways of calling functions. So BLX stands for branch with link and exchange, and it works the same way as BL, but if you're currently in ARM mode, you'll switch to thumb mode, and if you're currently in thumb mode, you'll switch to ARM mode. What about returning from functions? How do you know if the link register is pointing to ARM code or thumb code? The key to that is that both BLX and BL set the least significant bit of the link register based on the current mode. So if you're in ARM mode, when you call the BL or BLX, it will set the least significant bit to 0, and if you're in thumb mode, then it will set it to 1. Since instructions are at least 2 byte aligned, this is fine, you don't lose any information. When it comes to returning, there is this BX instruction, which branches to the address provided in the register, which is generally the link register, and sets the mode based on the least significant bit. Okay, on to exercises for ARM32 control flow. Okay, let's move on to memory and the stack in ARM32. And we'll start again by looking at the basic similarities and differences to ARM64. So LDR and STR work mostly the same. There's obviously no 64-bit variants of these. LDP and STP don't exist, but there's a different instruction that's capable of performing similar things, which we'll take a look at in a minute. ADR is the same, and ADRP doesn't exist. So we'll now look at something that exists in ARM32 but doesn't exist in ARM64, and that are these LDM and STM instructions, which allow you to basically load or store all registers at once. So RN holds the address you want to load from or store to, and registers is a list of registers you want to load or store. Now, register lists are something else that doesn't exist in ARM64. This is an example. It's basically a comma-separated list enclosed in curly brackets, and hyphens can also be used to specify ranges. One important thing to remember is that register lists don't preserve their order when assembled. The lowest numbered register will always be loaded from or stored at the lowest address. Also, you can't specify the same register more than once in a list. The last thing to address is this exclamation mark. If this is included, then RN is incremented by 4 times the number of registers in the list. In fact, LDM and STM are actually just shorthand for LDMIA and STMIA, with the IA standing for increment after. There are also variants for increment before, decrement after, and decrement before. Let's quickly look at the stack. There are a few minor differences to ARM64. This is how one might look. SP still points to the top. It's still full descending. Most of the time, the ARM32 stack only needs to be 4-byte aligned. Using what we've seen already, you might be able to work out the pushing and popping instructions. So there is just this push pseudo instruction, which is really just a STMDB, so store multiple decrement before with the stack pointer. And for popping, there's the pop pseudo instruction, which is really just a load multiple and increment after with the stack pointer. Looking at the call stack, the same-ish principles apply, but for non-leaf functions, the save frame pointer and link register is basically always at the bottom of the frame, and that's just because with the available instructions it's more efficient. So in the prologue, the frame pointer and link register are pushed. The frame pointer is set to the stack pointer, meaning it now points to the save frame pointer and link register, and the stack pointer is decremented to make space for local variables, etc. And the epilogue, the stack pointer is set to the frame pointer, and the save frame pointer and link register are popped. Note that the save link register is popped into the program counter, so this actually does the returning. It uses the same logic as BX, so mode transitions are handled where required. For leaf functions, just like at ARM64, these generally don't bother with saving the frame pointer and link register at all. In the prologue, the stack pointer is just decremented, and in the epilogue is just incremented, followed by a BX to the link register. Calling convention we'll cover very quickly. Arguments are passed in R0 to R3, followed by the stack. The return value is put in R0, or if it's larger, split between R0 and R1. And if it's even larger, then instead of passing an argument in R0, the caller passes a pointer to memory on their stack frame where the return value should be saved. The only caller save register is R12, and R4 to R10 must be saved by the callee. On to exercises, which are ARM32, memory and stack. For the last section, we'll look at miscellaneous things. For system calls, again, we'll only look at Linux. The syscall number goes in R7. Bear in mind that these numbers are different between ARM32 and ARM64, so you'll have to consult the relevant table. Arguments go in R0 to R5. The same SVC instruction is used to execute the system call, and the return value ends up in R0. In terms of PAC and BTI, They do exist in ARM v8m and work in broadly the same way. The instructions differ a little, but I'm not sure they're really worth talking about at the moment because I don't think this is particularly common to see this actually implemented. Okay, let's move on to x86-64. Again, we'll start with what is it? It was originally developed by AMD, then Intel also licensed it, and since then, both companies have extended it, each implementing each other's extensions, etc. They both produce their own processors, and they're used in most desktops, laptops, and servers. It's known by a few different names: x86-64, sometimes just x64, sometimes AMD 64, more rarely Intel 64. Like ARM 64, it's 64-bit, but unlike ARM 64, it has variable length instructions, and these can vary from 1 to 15 bytes. It's CISC, complex instruction set computing. It has some instructions that are very complex. I find this website to be the best reference. You can download a massive PDF from AMD or Intel, but this is a lot easier to navigate. So let's look at the instruction format because it differs a little to what we've seen before. So here's a typical add instruction. It's still an opcode followed by a comma-separated list of operands, but while in ARM 64 you typically had one destination followed by two source operands, in x86-64 the first operand will often double up as the source and destination. So this instruction is like saying RAX is RAX plus RBX. Now let's look at the general purpose registers. These are a bit more complicated than in ARM 64. There are 16 in total, and all of them allow you to access the full 64 bits, as well as the low 32 bits, the low 16 bits, and the low 8 bits. Additionally, RAX to RDX allow you to access the second to low 8 bits. A lot of the first 8 will have special uses in special situations, so for instance RSP and RBP are generally used for the stack pointer and base pointer, and some instructions may just expect an input to be in a specific register or put an output in a specific register, and we'll see examples of this in a minute. Another big difference is with what operands can be. So while in ARM 64 operands are generally registers, occasionally immediates, and there are only a few instructions that deal with memory locations, in x86-64 operands can generally be any of the three, so they can often be an immediate, a register, or a memory location. So for instance, you can directly add a register to a memory location, or a memory location to an immediate, or many other combinations. We'll talk about how you specify memory locations later on. Now let's look at the basic arithmetic operations. Add and sub are quite simple. Both operands can be a register or memory location, and the second can additionally be an immediate. We've already discussed that the first operand both acts as a source and destination, an input and an output. I find it helpful to think of the first operand plus equals or minus equals the second operand, if you're familiar with that syntax. A few notes, and these apply to most instructions. First, you generally can't mix operand sizes, so you couldn't add a 32-bit register to a 64-bit register, for instance. Second, you're generally only allowed one memory location operand, so it's fine to subtract a register from a memory location or a memory location from a register, but you can't subtract a memory location from a memory location. And third, immediates are generally limited to 32 bits, and their sign extended to the size of the other operands. Now, let's move on to looking at multiply, which is a bit odd. It has two variants, mul, which is unsigned, and imul, which is signed, and it's one of those instructions that just expects and puts things in certain registers. So it multiplies RAX by the operand, and because multiplying two 64-bit numbers can result in an 128-bit number, the result is split across RDX and RAX. So the most significant part in RDX and the least significant part in RAX. And the fact that it gives you this full 128-bit output rather than truncating it to 64 bits like an ARM64 is the reason that there are both unsigned and signed variants, because you need to either zero extend or sign extend the inputs up to 128 bits essentially. Divide is also odd. Again, there are two variants. This time the combined RDX and RAX is the dividend and the operand is the divisor, and the quotient is put into RAX while the remainder is put into RDX. Just a quick note, there are also these very simple inc and dec instructions which just increment or decrement the specified register or memory location by 1. Thankfully, the bitwise and shifting operations are quite a bit simpler. Not swaps the bits of a register or a memory location. And or XOR are quite self-explanatory. They have the same operands as add. SHL and SHR are your logical shift left and logical shift right. SAR is your arithmetic shift right, and ROR are your right rotate. These are a little odd. For the second operand, they accept an immediate or the CL register. No other registers are allowed. And for the final part of this section, let's look at moving things around. So in x86 64, this is quite simple. There's just this move instruction, which sets the first operand to the value of the second operand. And it also has a second variant, which allows you to set a register equal to a 64-bit immediate. And this is the only instruction that allows a 64-bit immediate. Alright, on to the exercises, which are x86 64 basics. Alright, on to control flow. So here's the infinite loop example in x86 64. Things work very similarly to ARM64. It's just that the instruction to go to a label is JMP for jump rather than B for branch. Just the same as in ARM64, when this is assembled, it becomes a relative jump, and disassemblers will generally show the operand as an absolute address. Worth pointing out that x86 64's version of the program counter is the instruction pointer, or RIP register, and yeah, it points to the current instruction just like the program counter did in ARM64. Comparisons and conditional jumps also look quite similar. So the comparison instruction is CMP. It takes the same operands as add, and it can be followed by one of the conditional jumps. I think these are a bit easier to understand than in ARM64. So there's JNE for jump equal, jump not equal. For the unsigned inequalities, the keywords are below and above. So JB for jump below, JAE for jump above or equal, etc. And for the signed inequalities, the keywords are less and greater. The way things work under the hood are almost identical to in ARM64, so CMP performs a subtraction and sets the flags based on that. The flags work the same, but they're named a bit differently. There is one significant change, and that is that most instructions in x86 64 set flags. There aren't any special forms like in ARM64, so add and sub, etc. will just set the flags. The documentation for each instruction will have a section detailing exactly how the flags are set. That being said, there are still a couple of common flag setting operations that it's worth talking about. First, there's test, which performs a bitwise AND on the operands and set flags based on the result. Since there's no CBZ or CBNZ equivalent in x86 64, this is commonly used to branch based on if a register is 0. So the register will be tested against itself, followed by a JE or JNE, which in this context is basically the same as jump if 0, jump if not 0. The other thing is ADC and SBB, which are add with carry or subtract with borrow. These are the instructions that include the carry flag in their operations, so they can be used to add or subtract large integers that are too big to fit in a single register. You'll notice that there's no conditional comparison, but x86 64 does have a couple of instructions that help with avoiding jumps. So the first of these is set, which can be followed by any of the same conditions as jump. The operand, which is an 8-bit register or memory location, is set to 1 if the condition is met, or 0 if it's not. And there's also cmove, which again accepts any of the conditions and only performs the move if the condition is met. That's it for this section. We'll look at how functions work in the memory and stack section. For now, there's exercises, which are x86 64 control flow. Right, on to memory and the stack. So we've already talked about how memory locations can be used in a lot of instructions, but how exactly do we specify them? This is the general syntax. This calculation will be performed, and the result of that is the memory location that will be accessed. Base and index are both general purpose registers. Scale can be either 1, 2, 4, or 8, and displacement can be any signed immediate up to 32 bits. It's important to note that you don't have to use the entirety of this equation, so you can remove basically any parts of it. So you could just have the base, or the base plus displacement, or the index multiplied by the scale, or whatever. Often when writing assembly, you don't need to specify the size of the memory location because it can be deduced from the context. So for instance, if you're adding a 64-bit register to a memory location, it can be deduced that memory location is also 64-bit. But sometimes, say for instance, you're adding an immediate to a memory location, the size needs to be explicitly specified. Also, it's fairly common for disassemblers to display this size for clarity. Doing this is quite simple. You just put one of these before the memory location calculation. So byte is for 8-bit, word for 16-bit, dword, i.e. double word for 32-bit, and qword, i.e. quadruple word for 64-bit. One final thing to talk about before we move on to the stack is this LEA instruction, which stands for load effective address. This performs the memory location calculation for the second operand, but it doesn't access it. Instead, it just stores the result of that calculation in the first operand. This means it's commonly used to perform certain mathematical operations very quickly. So here's an example where RAX is set to RAX plus RBX times 2 plus 7. Normally this would take multiple instructions and be quite slow, but thanks to LEA, it's a lot faster. Onto the stack, it looks very similar to ARM64. RSP points to the top, it's full descending, and it should generally be 16-byte aligned. This is more of a relaxed rule than in ARM64. Not every instruction will fault if it uses a misaligned stack pointer, but for some complex instructions they do require their memory locations to be 16-byte aligned, so it's part of the convention that the stack's also 16-byte aligned. Pushing has its own instruction. Only 64-bit registers and memory locations are allowed, and immediates are sign extended up to 64 bits. The same applies for popping. Calling and returning from functions is a bit different in x86 64, which is why we've waited until now to talk about it. The call instruction pushes the return address to the stack instead of putting it in a register before jumping to the label, and the ret instruction pops from the stack into the instruction pointer. Now let's see how that's reflected in the call stack. So here's what the frame for a non-leaf function typically looks like. The return address will be the topmost item in the previous function's frame. In the prologue, the base pointer is pushed and then updated to point to the safe base pointer before the stack pointer is decremented to make room for local variables, etc. There's actually one instruction that does all of this called enter, but no compiler will ever use it since it's slower than the push move sub combination. In the epilogue, the stack pointer is incremented to get rid of the space before the save base pointer is restored, and we return to the address on the stack. Leaf functions can look a bit different. There's something called the red zone, which means that it's safe to access 128 bytes beyond the stack pointer. So if a leaf function has less than 128 bytes of local variables, it will typically just use that red zone space and won't bother with decrementing the stack pointer at all. For the last thing, we'll quickly look at the calling convention. This is the system V calling convention. It's the most common one you'll see on Linux. Arguments are passed in RDI, RSI, RDX, RCX, R8, R9, followed by the stack, and the return values put in REX, or if it's larger, split between REX and RDX. If it's even larger, then instead of passing an argument in RDI, the caller passes a pointer to a memory location in their stack frame, and that's where the return value will be saved. R10 and R11 are caller saved, whilst RBX and R12 to R15 must be saved by the callee. So on to the exercises, which are x86, 64, memory and stack. On to the miscellaneous section, still only look at Linux system calls. So the system call number goes in REX. Again, x86 64 has its own table of system calls. Arguments go in RDI, RSI, RDX, R10, R9, R8. To execute the system call, there's just this syscall instruction, and the return value is put in REX. x86 64 is equivalent to PAC and BTI, is called CET, or Control Flow Enforcement Technology. There's this end BR64 instruction, which maps pretty much to the BTI instruction in ARM. It marks a valid target for an indirect branch. There's no pointer signing, but to protect the return address, there is something called the shadow stack, which call will push to as well as the regular stack, and then return will compare the values on the top of both stacks and fault if they don't match. And that's it. Thank you very much for watching.